Welcome. As you're about to find out, if you haven't already, Chapter 1 from our calculus text is just a whole lot of review of things we've done. And as you can see right at the beginning, we're just writing equations of lines, being given some different informations. But this will move pretty rapidly into some concepts that we probably need to review. But I'm going to go through this fairly quickly. So we're going for slope-intercept form of equations of lines. First, passing through a given point and a slope. Well, if I am given a point and I'm given a slope, I'm of course going to be tempted to use point slope form, which is y minus the given y coordinate equals slope times x minus the given x coordinate. I just call it puzzle pieces. We just got puzzle pieces to put in to these givens. So we end up with y minus the y coordinate, -6, so y plus 6 equals 3 times x minus the given x coordinate, 1. And if the directions just asked for an equation of a line, I would stop there. However, slope-intercept form, of course, is y equals mx plus b, m being our slope, b being our y-intercept. So basically, slope-intercept, I often say slope-intercept starts with s. You can think of that as standing for solve for y. So to solve this equation for y, I might be tempted to distribute the 3 first, and then of course subtract 6, and I end up with y equals 3x minus 9. This is not particularly calculus material, but certainly something that we better be very, very good at. Okay, easy as it may seem, this often gets missed. We're looking for equation of a vertical line through 0, -3. Here's my x coordinate, here's my y coordinate, and hopefully at this point, for certain that we know that this is either x equals 0 or y equals -3. But the graph can be very helpful. If we just take a look at this, we've got a point at 0, -3, and we want a vertical line that passes through 0, -3, so our line is this. And I'll still get people that even from the graph will miss it, and they'll say, well, it's vertical, so that means the y's are changing all the time, so this must be a y graph. Well, let's put another point on this. Right here is the point 0, 2. And what do we notice? No matter where we go, x equals 0. So x equals 0. Okay, number 5, horizontal line. Again, I'm going to go back through the graphing process just to kind of emphasize that. You may not need to do this. We have a point at 0, 2, and now we're horizontal through that point. Here's another option of looking at it when we have the graph. I say, well, what is not changing? What is constant all the time? The height is always 2. This graph is always up 2. Well, the height is always 2. Y equals 2. That's terrible, 2. Y equals 2. You could, if you're thinking of this one in those terms, you would say the graph is always to the right 0 or always to the left 0. Our right-left variable, x, is always 0. Okay, well, 7 to me seems like maybe 7 should have been number 1. We're just supposed to find the equation, the slope-intercept equation, and they actually give us the slope. They give us the intercept. So y equals mx plus b just becomes y equals our slope, 3, times x plus -3, but you're gonna lose points if you leave double sign. So of course y equals 3x minus 3. I would certainly not expect you to show work beyond just this on a problem that simple. Okay, number 9. Line passes through a point. Well, if they give me a point it passes through, that's 2/3 of my puzzle pieces right here for point slope form. So if I can get a slope on parallel to, and I know if lines are parallel, they have equal slopes, so I need to find the slope of this. To find the slope of this, we might want to solve for y. So I get 3y equals subtract 4x on both sides, joins a plus 12, divide both sides by 3, y equals negative 4/3 x, and really I could stop there, plus 4. The slope we want to use is negative 4/3. So now I have my puzzle pieces. I have an x, I have a y, I have a slope. So put my puzzle pieces in place here, and I've got y minus my y coordinate, y minus negative 12, y plus 12, is slope negative 4/3 times x minus our given x coordinate minus 4. And I want to solve this for y. How about we distribute? Y plus 12 equals negative 4/3 x minus times minus plus 4 times 4/3, 16/3. I'm going to subtract 12 to get y alone. Subtracting 12, of course, is subtracting 36/3 to get common denominators. And I have y equals negative 4/3 x, 16 minus 36 minus 20/3. All right, same problem, except what do we know about perpendicular slopes? Perpendicular slopes are opposite reciprocals of one another. But I know this before I even start. I'm going to set this up as y minus 2 equals something times x minus negative 1, x plus 1. I just need slope. Now, if fractions are intimidating to you, the nice thing about getting good at algebra is oftentimes you don't have to work with fractions until like maybe a last step. If you wanted to, and I'm not suggesting you need to do this, you could start this by getting rid of fractions, multiplying both sides of the equation by our least common denominator, 6. When I distribute 6 to the first term, 6 divided by 2, 3, I get 3x. When I distribute 6 to the y's, 6 divided by 3, 2y, equals 6 times 1, 6. Again, I'm not saying you have to do that, I'm just showing you something here. I want to get y alone, subtract 3x, subtract 3x. I have 2y is negative 3x, joins a positive 6. Divide 2, and really at this stage, I've got what I'm looking for. I've got my slope, negative 3/2, passes through this point, so negative 3/2. Solve for y. Y minus 2 equals negative 3/2 x minus times plus minus 3/2 times 1. Add 2, that's adding 4/2, and I get y equals negative 3/2 x, negative 3 plus 4, positive 1/2. And there you have it. Okay, let's continue on with this. This is still in the same topic. We're supposed to find the equation of the line that has these points. So we put x into this function, negative 2, we get out 4. We put 2 in, we get 2. 4 in, we get 1. We could graph this and study the graph, but I could also say this, hey, my line passes through the point 4, 1, for instance. So that's y minus a y coordinate 1 equals m, I don't know, times x minus the x coordinate that goes with it, 4. Obviously we could do this with any of those 3 ordered pairs. What I need is slope. Of course we know that slope is the change of y over the change of x, and we can use any consecutive points here. Just so these points don't feel left out, finding slope, I'm going to use these. So my y changed into 2. It started out as 4, as my x changed into 2, it started out as negative 2. So I just went 2 minus 4, change a y, over 2 minus negative 2, and I get negative 2 on 4, or negative 1/2. And there we go, I got my missing puzzle piece. Distribute, y minus 1 equals negative 1/2 x minus times minus plus half of 4. 2, I'm going to add 1 to both sides, and I get y equals negative 1/2 x, adding 1 plus 3. Okay, I realize, my guess is many people who view this probably will skim through this, but if that was helpful, a little bit of a reminder, great. At this point, there may be some things that are worthy of reviewing, because I believe some of these topics from this point on, last year was your first exposure to them. If you took honors pre-calculus with me, then I'm going to speak the same language. If you took it with another teacher, Mr. Hartz, I believe he might have spoken the same language as well, as I talk about graphs. Determine if the graph is symmetric to the y-axis, to the origin, or neither. And we're not going to rush to our graphing calculator here. Now, we could kind of do a little mental t-chart, and I could say, well, let's just take a look at the graph. I know if I put in 0, I get out 0. I know if I take the 5th root, or 1 to the 1/5, I still get out 1. And I know if I take negative 1 5th root, negative 1 to the 1/5 power, I get out negative 1. I'm pretty convinced at this point that there's a very good chance that this is symmetric to the origin. My next really good 5th root is 32. Is that right? 2, 4, 8, 16, 32. Yep, the 5th root, or 32 to the 1/5 power, is 2. So I'd be all the way over here to 32 before I'd get up to 2. And negative 2 is equal to the 5th root of negative 32. And now I'm starting to really believe, yeah, I believe this guy is symmetric to the origin. Okay, your day 1 honors pre-calculus lesson last year was very likely this. We talked about sprinters, intermediate runners, distance runners. For those of you who don't speak that language, you could come up with another way to graph this, but I know when x is 0, I'm at negative 1. This guy's in charge. And then I know this wants to look like a line going down with a slope of negative 2. So this one wants to start us at negative 1. This one wants to be a line going down, but ultimately the x squared is going to take control and is going to make this one look like this. So this guy just in general must look something like that. And I look at that, and that is most definitely not symmetric to the y-axis. And it doesn't spin around the origin onto itself either. Therefore, this is neither. Even or odd or neither. So even functions are symmetric to the y-axis. An even function. Here's a typical even function. Our plain old parabola that we're really like y equals x squared. It flips onto each other. The rule states that a function is even if the height going to the right is the same as the height of the graph going to the left. That's an even function. So if I want to know if the height to the left is equal to the height of the right, and I don't know what the function is, then I can put a right hand value in for x and a left hand value in for x. Something like this. If I call, let's say y1 is equal to x squared plus 2. Let's say there's another point y2 that's equal to leftward the x value plus 2. Well, real quickly we can see this can simplify into x squared plus 2. Therefore, if I put in 7 here, put in negative 7 here, or put in negative 7 here as well, I get the same value out. Therefore, if I go to the right, I get the same height as I get going to the left. If you want to go to the graph, this graph starts up 2 and then looks like a parabola. Oh yeah, that's symmetric across the y-axis. So this function is even. Okay, 21. I'm hoping that everybody remembers that the graph of cosine looks like this on and on and on. That function as it stands right now is symmetric across the y-axis. That would be even, but how about this one, 1 minus? I might think of this as negative cosine of x plus 1. So do we remember our transformations of graphs? This graph wants to look like cosine. I put x in, I get out a height of a graph, and then I get the opposite height. Oh, so this graph is upside down. And then I raise it up 1. So this graph upside down and up 1, this point would go upside down to here, it would go up to here. This point upside down stays here, up 1 would take me up to there. This point upside down would be up 1, and up another 1 takes me up to here. This graph looks like this. This point upside down stays the same, up 1. Oh, I'm getting a feel for what's going on here now. This graph looks like this, on and on. So it stayed even because it is symmetric across the y-axis. Okay. Let's go back and talk about odd functions. I'm not necessarily suggesting that the next function is odd, but maybe a really common odd function is like y equals x to the third. Looks something like this. Oh, odd functions are symmetric about the origin. This is an odd function. This function kind of wants to be even, but it's not even. It's symmetric across this line, but it's not even. It needs to be symmetric across the y-axis. Okay, so this guy, well, I don't really necessarily, it might take me a while to figure out what this graph looks like, so I'm going to do this from an algebraic perspective, kind of like what I did here on 19. I know when I put, let's consider x as a positive value. I know when I put a positive value in, I get this. When I put a negative value in, let's see what happens. I get negative x, got to take that to the fourth, plus 1. On negative x, got to take that to the third, minus 2 times negative x. Let's see what that simplifies out to be. Well, negative x to the fourth, the negative gets absorbed, so that's just x to the fourth plus 1 on negative x to the third would become the opposite of x to the third. Minus 2 times minus x is plus 2x. So here's what I just learned. There is no way you're going to convince me that this is equal to that. Therefore, when I go to the left, put in a negative, I'm not going to get the same value as when I go to the right. This is not even. Is it odd? Well, an odd function. If I go, like if this was y equals x cubed, there'd be a point 2,8 here, and there'd be a point negative 2, negative 8. If I go to the left, I should get the opposite height as if I go to the right. So are these exact opposites? And here's how we test that. Well, what if I put, what if for them to be opposites, like 7 is opposite of negative 7. I'd multiply by negative 1. So if I take this thing times negative 1, can I make it become this? Well, if I multiply by negative 1, my choice is either multiply by negative 1 on 1, and then I'd get negative x to the fourth minus 1 over x cubed minus 2x. Or I could multiply by the negative in the denominator, and I would get x to the fourth plus 1 over negative x cubed plus 2x. This function is odd, because when I go to the right, I've determined these are opposites. I get the opposite of what I get when I go to the left. Okay, let's try that with this function. How about I put in a negative x? Y equals negative x plus cosine of negative x. All right, let's go back up to our cosine graph here. Cosine of negative x. Well, cosine of negative x, I'm just making my x's go in the opposite direction here. It's backwards, but backwards this, what do we notice about backwards this? If I turn this backwards, I get the same graph. So I get that graph, and now I'm subtracting my x values. So the bigger the values I get for x, the more I'm adding to this a big negative value, if that made sense. The graph of negative x wants to look like that. The graph of cosine negative x wants to look like this forever. So we're going to get this, by the time I put 100 in here for x, x wants to, of course, be going up. By the time I put 100 in here for x, my graph's going to be 100 plus whatever cosine of 100 is. So it wants to kind of be a cosine graph doing something like that, moving up in an xward direction. So it most definitely is not even. It's just a discussion, is it odd? And maybe we would want to start taking a look at that on a graphing calculator, but let's ask this question. Y equals negative x plus cosine of negative x. That is the same as y equals negative x plus cosine of positive x, because cosine to the left is the same as cosine to the right. Is this function the same as that? Of course not. Is this second function equal to the first function times negative 1? Times negative 1? No, it's not. It would have to be negative x minus cosine of x. So this is a neither. A little bit of work involved there. Okay, we got 6 more problems we're going to take a look at in this video. Number 27, we are to find the domain, the range. Domain's pretty easy. Domain is what value can I put into the function for x, and we couldn't calculate with it. Our calculator would give us an error. So I just take it step by step. Can I take the absolute value of any number I want? Can I take the absolute value of a positive? Can I take the absolute value of a negative? Can I take the absolute value of 0? And the answer to all of those is yes. Next, can I subtract 2 from any number I want? Of course I can. Therefore, my domain is all real numbers. Now, range is the kind of values that come out. What values come out of absolute value? Well, I can never get a negative out of absolute value. I can get out a 0. So if I put 0 in, I get 0 out here and subtract 2. I'm claiming the smallest number I can get. So the smallest number I can get for y is 0 minus 2, negative 2. Therefore, y is either bigger than or equal to negative 2. If we look at this from a graphing perspective, and I'll do a quick mental t-chart with you. Put in 0, get out 0, minus 2, negative 2. Put in 1, get out 1, minus 2, negative 1. Put in 2, get out 2, minus 2, 0. Put in 3, get out 3, minus 2, 1. I got an idea what's going on here. Put in negative 1, comes out of absolute values as positive 1, minus 2, negative 1. Put in negative 2, comes out 2, minus 2, 0, and we've got this. From a graphing perspective, domain and range are a breeze. Look, this graph's going to go on forever. It never stops. It never jumps. It's right and left forever. But the y values are always at least negative 2. All right, domain, range, number 29. Can I take any number I want to the fourth power? Yes. Can I subtract any number I want? Yes. Can I take the square root of any number I want and get a real number answer? No, I can't take the square root of negative. Therefore, in our study for domain, I'm interested when x to the fourth minus 1 is bigger than or equal to 0. I can take the fourth root of 0, or excuse me, the square root of 0, but I can't take the square root of a negative. So this gives me x to the fourth is greater than or equal to 1, or x is greater than or equal to not just the fourth root of 1, but plus or minus the fourth root of 1. Oh, well, that's not even really true anymore with this greater than or equal to. Let's take a look at this on a graph, because the fourth root of 1 is plus or minus 1. So let's look at this on a number line. Here's 1, here's negative 1, here's 0. Okay. If I put 0 into this, will my calculator have any problems with that? I get 0 to the fourth, 0 minus 1, negative 1, square root of negative, oop, I can't be in here. If I put 1 in, am I okay? Just barely. If I put negative 1 in here, am I okay? Negative 1 to the fourth, 1 minus 1, 0, just barely. If I put 2, I get 2 to the fourth, 16 minus 1, square root of 15, no problem. If I put negative 2 in, I get negative 2 to the fourth, 16 minus 1, square root of 15, no problem. Therefore, our domain, I'm going to write that in interval notation. Watch this. I can move from infinity, negative infinity, all the way up, negative infinity, all the way up to negative 1, and I can touch negative 1, that's the bracket, or union, I can start again at 1 and continue on to infinity, use a parenthesis because we never get to infinity. So, a little sneaky there. How about range? Well, ultimately, my last step in getting the range, I'm going to take the square root. And square roots, I don't get negative numbers out of primary square roots. So our range, can I get 0 out of this? I can get 0 out of this. Can I get a negative? Nope. So our range is 0 to infinity. Now, if we graphed it first, it's actually easier to find those things. So I'm graphing this thing first. We'll just make a small sketch down here. I'm just going to mental t-chart here. Put in 0. Oh, can't put in 0. Put in 1. I get 1 to the fourth, 1, minus 1, 0. So 1 gives me 0. If I put in 2, I get 16. 2 to the fourth, 16, minus 1, 15. Square root of 15, well, square root of 16 is 4, just a little bit less than 4. So somewhere down in here. So I know on this side my graph's doing something. It's heading up. I don't know, do we have the curve right? You can give some thought to that. Put in negative 1. Negative 1 to the fourth, 1. Minus 1, 0. Put in negative 2. Negative 2 to the fourth, positive 16 minus 1. Square root of that, a little bit less than 4. We're heading up here. Somehow or another, I don't know, how's it curved? You can put some thought to that. But you see now my domain is clear. My domain, my x values start at 1, go forever to the right, start at negative 1, go forever to the left. My range hits 0 and heads up. Okay, oh no, E, how in the world are we going to graph when we get an E number in there? It doesn't matter. An E number raised to a power is always going to be positive. A positive number raised to a power, I don't care whether it's a negative power or not, is always going to be positive. So this part right here, the confusing part, is never going to be 0. Always going to be positive, which means this, when I multiply it by 2, can get really close to 0, but it's never going to be negative, it's never going to be 0. If this part gets really close to 0, then my y value is going to get really close to 0 minus 3 or negative 3. My range is going to get close to -3 but never quite get there. But this number can get big. Like if I take e to the -0.1, that's like taking e to the 10th. This number can get really big and subtract 3 from, so we can approach infinity. How about this domain? Can I take e to a positive power? Yes. To a negative power? Yes. To a 0? Yes. So this is all real numbers. Now, graphing this. This part, if we're going to graph it by hand, not the easiest thing in the world to do, but we can certainly do a little bit of a sketch here. I'm going to start with 0. I'm just going to do a mental T-chart again. I'll show you how we're going to work through this. A mental T-chart here tells me if I start with 0, e to the 0th is 1 times 2, 2. We're at -1. Okay. Now, I know my range. I can't get to -3. This is an electric fence here. I can't touch that. All right, let's put in 1 and see what happens. You're like, well, how can I figure out what this is? Well, let's say e is a little bit more than 2. Well, a little less than 3. Let's just say e's more than 2. Since e's more than 2, 2 times, well, when I'm putting in 2, sorry, let me back up on that. A little more than 2 to the -1st, because I'm putting 1 in for x. So a little more than 2 to the -1st is 1 on a little more than 2. And so that's 2 times 1 on a little more than 2. Well, 2 over a number that's bigger than 2 is a little bit less than 1. So we're up here. Okay. Oh, then I have to subtract 3 from that. Sorry. Subtract 3, and we're down here, down 1, 2, 3, a little more than -3. So I got a real quick feeling this is going to get sucked into this asymptote. And when I put negative value, let's put in -1. That's actually easier. When I put -1 in here, I get e to the positive first. More than 2 times 2, more than 4 minus 1, minus 3, more than 1, we're heading up. So there's a approximation of a graph. Okay, how about this? Can I multiply any number I want by x, or by 3? Yeah, any number. Positives, negatives, 0. Can I add pi to any number I want? Yeah. Can I take the sign of any number I want? Yeah, the graph of sine lives on forever. The graph of plain old sine looks like this. It doesn't mind any values of x. I'd never have to pick up the pen as I'm graphing sine. So that is all real numbers. Now, for the domain, or for the range of sine, well, the range of sine, typically it goes up to 1 and down to -1, and it touches both. Does this 3 affect the range? If you were with me last year, I would say this 3 times is a pre-function. That affects what's going on x. That either widens the graph or narrows it or moves it to the right, left. That's a pre-function. Plus pi is a pre-function. These do not affect the range. This says, hey, once we're through here, we're going to say the graph of this looks just like sine, except it's 3 times as tall. So instead of going up to 1 and down to -1, it would be 3 times as tall, up to 3, down to -3. And this lowers it. Those are post functions. So instead of going up to 3, this graph is going to go up to 2 and touch it. Instead of going down to -3, it's going to go down to -4. And I'm going to leave the graphing of this. We'll talk about that quite a bit to another time, another discussion we'll have on graphing this thing. Okay, number 35. Can I subtract 3 from any number I want? Sure, I can subtract 3. Can I take the natural log of any number I want? No, I can only take the natural log of positive numbers. Therefore, x minus 3 has to be bigger than 0. X has to be bigger than 3. That is our domain. We could also, in interval notation, call that 3, not touching it, to infinity. Interval notation is definitely preferred in calculus. Okay, range. Range. What is the biggest or smallest value that's going to come out of ln? Well, can ln be a negative? Gee, this is ln of x minus 3 is the exponent that turns e into x minus 3. So this is an exponent. Can I have negative exponents? Yeah, this can go up and down forever. Hopefully we know a plain old logarithm graph looks like this. Any logarithm graph, just ln of that or ln of x or log base 7 of x, they all look like this. Therefore, we can get negative infinity to infinity. So our range is all real numbers. And the graph. Let's go back to what we know about our graph or just plain old ln. Y is ln of x. That would be, if I put in 1, the exponent that turns e into 1 is 0. If I put in over here at e, between 2 and 3, if I put e in here for x, the exponent that turns e into e is 1. And I can't have x be 0, so plain old ln of x looks like this. How will this graph compare? Well, there's a pre-function. That makes my MIVOX, my most interesting value of x, 3. My most interesting value of x was most definitely 1. Well, now it is 3. Plus 1. That's a post function. All my values raise up 1. What was here at 1, 0 goes over 3. 1, 2, 3, up 1. What was here over e goes over 3 more from there. So between 2 and 3, over 3 more from there, 1, 2, 3, and up from 1, up 1 more up here. So our graph looks like that. So it's right 3, up 1. This point went right 3, up 1. We got to this point by starting here, going right 3, up 1, and our asymptote went right 3, and if you like, up 1. Okay, number 37, hopefully we remember this is called a piecewise function. This says we can put values of -4 and up to 0, and then 0 up to 4. We can put those in. That tells us what our domain is right away. Our domain, I'm only allowed to be -4, and I can be -4, up to 0, but I include 0 here. I don't here, but 0 is included in this. I can put 0 in this function, and then I can continue up to 4. Therefore, in interval notation, I would write this as I can touch -4, and I can continue going to the right until I touch 4. Okay, domain. Let's jump to the graph of this first. Let's go ahead down here. Let's graph this, and let's take a look what we get. I'm going to go ahead and just do a mental t-chart with this. If I put -4 in here, if I put -4 in for x, I get the opposite of -4, 4. 4's square root is 2. Well, that was convenient. If I put -3 in, I get the absolute value of 3. Or excuse me, the square root of 3, I'm sorry, which is about 1.7. If I put 2 in, -2, I get the square root of +2, about 1.4. I'm still up in here. If I put 1 in, I get -1 in, I get the square root of +1, 1. And if I put 0 in, I get 0. So this graph looks like this, but no arrows on it. It definitely stops. at those points, particularly this one. Then if I move to this and I put, if I was allowed to put 0 in here, I'm going to do this in black. If I was allowed to put 0 in here, I would get 0, so that would really be an open circle. When I put 1 in here, I get 1. When I put 2 in here, 3 in here, 4 in here, by the time I put 4 in here, I'm up to 2, and then I stop. Whoops, I said it earlier, it stops there. Those are stopping points. So ultimately, my graph comes here, and that is filled in, and comes up to there. Okay, pretty easy to see. Domain starts at -4, continues until we get to 4. Range starts at 0, including 0, goes up to 2, including 2. So our range is 0 to 2. Okay, I hope that's helpful. I know that's a long one. My guess is there's a lot of that was really, really simple for you early on, and I'm sure there's something that maybe everybody could get out of that later. This is material that you're going to be tested on from Chapter 1 very soon. We're going to give you some practice problems that you can work on those. There's another video that will accompany this with a little bit more Chapter 1 material. Thank you.